Okay, good afternoon, everyone. Welcome to the Third Coast Water Seminar. My name is Elena Harkness, and I'm the Executive Director of Current, Chicago's Water Innovation Hub. And on behalf of the partners on screen, Northwestern University, the University of Illinois Urbana-Champaign, Argonne National Laboratory, the University of Chicago, and the University of Illinois at Chicago, I'm really excited to welcome you here for a great conversation about the hydrologic performance of the green roof on the Nicholas Pirro Convention Center in Syracuse, New York. This is your first Third Coast Water Seminar. Just a few logistics for you today. We will take questions in the Q&A tab and general comments in the chat. As always, these events are being recorded, and the recording link is always shared out on Current's events page and our YouTube channel, so you can access it after the program. As always with the current Third Coast Water Seminar, we have a very tight agenda for you. I'm going to have a few opening remarks from one of our Third Coast founders, Brian Chaplin from the University of Illinois at Chicago. He's going to introduce our featured speaker today, Dr. Cliff Davidson of Syracuse University. We'll have a feature presentation from Cliff and then audience Q&A and wrap you up just before the top of the hour. But first, a few remarks about Current, who we are and what we do. Current, Chicago's Water Innovation Hub. We're 5 years old this year, and we have a three-part mission: grow an inclusive blue economy, accelerate innovation in water technology, and solve persistent water challenges. Why are we here? We're here because we know that we all need more healthy water to drink and less flood water in our basements. These common challenges that facing residents all around the world come to ground right here in our backyard in Chicago. We also know that we need more blue jobs, putting Chicagoans to work, and homegrown companies solving water challenges all around the world. At Current, we believe that there's an urgent need to rally faster behind the new ideas and technologies that will protect our health and environment. We know that water problem solving is challenging, and it almost always requires collaboration. So Current is purpose-built to support partnerships and sustain them between industry, government, nonprofits, businesses, and the research community, all of whom are trying to figure out how to take more rational risks to try out new solutions and bring them to market faster. The way we work is to be an unbiased advocate for the best water solutions and policy. So it's our job to stay on top of the latest in water tech, knowing this field is rapidly changing and multidisciplinary, and then independently assess these technologies to understand which might be the best for others to try in their sites, whether it's utilities or corporate partners, or for us to pilot on our own, like our water quality project that we'll be launching soon in the Chicago River. We're also much more than a connector. We actually test new technologies in the real world. What you see here is, again, a piece of that river water quality monitoring project, H2 Now Chicago, where we're actually developing a set of technologies to help test and share the real-time water quality in the Chicago River with the public. We're working on an evolving array of issues because the needs of our region are changing all the time. Sewage surveillance is one that we're working on right now, using wastewater as an early warning indicator for SARS-CoV-2 and other public health issues. PFAS elimination, targeting and eliminating forever chemicals, and finding ways to better recover heat energy from wastewater. Renewable energy and meeting our climate goals, obviously a very important topic on all of our minds. And for all of those reasons and more, we are always excited to bring the best minds from all around the world here to the Third Coast Water Seminars, here to Chicago, to tell us what they're learning and help us understand how we can translate that into actionable solutions for our region. So with no further ado, I'm going to introduce my friend and collaborator, Brian Chaplin from the University of Illinois at Chicago, to introduce our speaker. Brian?
Yeah, thank you, Elena. It's my pleasure to introduce the speaker today, which is Cliff Davidson from Syracuse University. Cliff is the Thomas C. and Colleen L. Wilmot Professor of Engineering, in the Department of Civil and Environmental Engineering, and the Center of Excellence in Environmental and Energy Systems at Syracuse University. He received his BS in Electrical Engineering from Carnegie Mellon and his MS and PhD in Environmental Engineering Science from Caltech. He served on the faculty at Carnegie Mellon for 33 years before moving to Syracuse University in 2010. Cliff's research is broad. He has considered sources and ultimate fates of environmental pollutants, design of cities to promote sustainability, innovations in engineering education, and various other topics. He has published over 140 journal publications. He has several books to his name, and also numerous awards for research and teaching. I was on his website this morning, and I noticed he's also an avid marathon runner. I didn't count how many he had run, but it looks like dozens of marathons to his name as well. So he really is an all-around talent, and we are very happy to have Cliff and look forward to your seminar. Thank you.
Thank you very much, Brian, and thank you, Elena. It's really a pleasure to be here. I'm going to share my screen and start the slides. Let's see. We are going to start here. Okay. As Brian mentioned, we're going to be looking at the performance of a green roof here in Syracuse, which is, as it turns out, one of the largest green roofs in eastern US. It's roughly 1.5 acres. This is a roof where I can have a large number of students working with me up there, and we can get a lot done on different parts of the roof. Okay, let me see if I can advance the slides.
Great, and Cliff, I don't know if this will change, but right now we're seeing a bit of your text cut off, so it doesn't look like we're getting 100% of the slide in view.
Oh, okay.
Out a little bit, that'd be great. There, perfect.
Okay, how does this look?
Perfect, thank you, great.
Okay, great. What is the problem we're trying to solve? Well, green roofs, as many of you know, are very important in terms of stormwater management. And I want to kind of back up a step and ask the question, what is green infrastructure? Because green roofs is only one type of many different types of green infrastructure, all of which are related to trying to manage stormwater in cities. We're going to cover several different topics in this talk. First of all, we'll discuss what green infrastructure is. Then we'll look at the traditional methods for stormwater management. That is popularly known as gray infrastructure. Then we'll focus on one particular type of green infrastructure, namely the green roof, and in particular the green roof on the convention center. We'll talk about how it performs, and we'll look at some data. And then how do we understand that performance of the green roof? So we'll look at some models that we've run versus measurements. And you can get an idea of how large this green roof is by looking at the photograph on this slide. And just for reference point, we are actually, this photo was taken in the spring. So the sedum has just recently flowered. There are 6 different species of sedum on this green roof. There are no other plants intended except sedum. You can see some of our equipment. They're slightly to the left of center, although we have equipment all throughout the roof, and we have a lot that's buried underneath the soil. This is a picture facing south from the north end of the roof. So you're getting an idea of the full size of the roof here. Okay, when we talk about green infrastructure, we really mean infrastructure that is resilient. And the meaning of resiliency is basically that whatever it is that's resilient is able to adapt to a variety of disturbances and can recover from disturbances, and also has a capability to mitigate against the risks and unknown incidents that might occur. So in the context of infrastructure, when we talk about resiliency, we are really talking about the concept behind the purpose of infrastructure, which is to deliver a service. So as long as the infrastructure is able to recover from a disturbance and can continue delivering its service, then this is considered resiliency, even if the infrastructure may look completely different and even may behave and perform completely different than before the disturbance. So as long as the infrastructure can perform this service, it is considered resilient. What are some examples? Well, I've just listed 5 here, and you can read these. The main idea here that you notice immediately is that we are talking here about vegetation. We're talking about green, meaning green plants. So actually, green infrastructure in general usually means a living system, and that has some profound implications. If we look at green infrastructure as a living system, this gets us to the concept of ecosystems. There are not many systems that humans have built that, in fact, are truly resilient. In fact, I could go out on a limb and saying, gee, we have never been able to build a system that is truly resilient. However, it is true that ecosystems are resilient, and that doesn't mean that they are efficient in terms of air, water, energy, materials, and so forth. In fact, there's a whole lot of redundancy, which generally means the opposite. It means a certain level of inefficiency. If one species of plant or animal dies out, then the function of the ecosystem can indeed be replaced by that particular function, can be replaced by another species. However, what we know from looking at the history of this planet is that ecosystems have been able to continue indefinitely. Not all components, but the ecosystem as a whole. This last bullet item is important to realize that in some cases, we call things green infrastructure, even though it does not actually have living components like vegetation. And permeable pavement is one of those. But in that case, permeable pavement is called green infrastructure because it's intended to mimic living systems. And in this case, permeable pavement is intended to mimic the natural soil, which of course has both living and non-living components. And we know that water can infiltrate through permeable pavement in much the same way that it can permeate or infiltrate into soil with vegetation or without vegetation. Okay, so the problem to be solved here is managing urban stormwater. And okay, Brian mentioned that I was at Carnegie Mellon for a number of years. And this photograph actually is one that I took when I was living in Pittsburgh. What you're looking at is the remnants of a parking lot that was about 20 years old. That parking lot was at actually it was a set of movie theaters that went bankrupt perhaps 30 years ago. And as a result, the building was vacant and the parking lot was not used for about 20 years of the time that I lived in Pittsburgh. And you can see that nature is starting to reclaim this parking lot. So nature is far more resilient than, say, a system such as buildings with a parking lot, which is a system that we have constructed. And you can read essentially the issues that are involved here and why we have a problem managing urban stormwater. We've got more impervious surfaces and we've got a lot of gray infrastructure that is aging, plus what we had prior to that development was natural vegetation, or in some cases farms. And now, to make it even more difficult, we've got a greater intensity of rainstorms and more frequent rainstorms due to climate change. So all of these contribute to the challenge that we face. If we look at the increased impervious cover, we can see the changes in the hydrologic cycle. So when we've got natural ground cover, which is on the left, we have roughly 50% of the water that falls as precipitation being infiltrated. And about 10% becomes runoff, goes into rivers and lakes, and about 40% evapotranspires back into the atmosphere. If we look in contrast at an urban area, and here you can see 75% to 100% impervious cover, which is typical of heavily urbanized areas. Instead of having 50% infiltration, we've got only 15% infiltration, and 55% runoff instead of 10% runoff. So this changes the dynamics of the hydrologic cycle very significantly. What are the implications of these changes? Well, obviously, all of you, I'm sure, recognize the importance of flooding as a big problem with our new increased frequency and increased intensity of rainstorms. And as well, we've got contaminants that go into our surface waters. We are not recharging our groundwater as we would be doing in a natural environment. And then finally, combined sewer overflows now becomes a serious problem. And so let's take a look at combined sewer overflows for a minute, because they have really become a mainstay in urban areas. A lot of urban areas have combined sewers. So that means that those sewers are intended to carry stormwater as well as the sewage that is coming from our wastewater generation. If the capacity of the sewage treatment plant is exceeded, then there is no place to put all that raw sewage in the wastewater. And so we're not able to treat it because the sewage treatment plant does not have the capacity. So with no place to put it, all we can do is divert it into the receiving waters. We're not talking about a small number of towns and cities here. That number from EPA is 770 towns and cities in the US that have this problem with CSO events. And this diagram shows I think pretty well what happens when there's a combined sewer overflow. So I'll point out that over on the left side of the screen, you've got a little house there, you've got a brick building, and you've got a street with street storm drains that are labeled, and water that is both wastewater as well as street storm drain water goes into the combined sewers. So you can see there that the combined sanitary waste and stormwater go into the sewer system. And then if you look to the right, you see that there is a weir to basically prevent the combination of wastewater and stormwater from going out into the receiving waters during normal times. By normal, I mean that the rainfall is small, or perhaps there's dry weather, and therefore the wastewater treatment plant, which is up in the upper right corner of the slide, is able to handle all of the wastewater. And if it's a light rain, that wastewater mixes with the stormwater, but it all can be treated. Once the water level rises above the height of the weir, then we know that the wastewater facility cannot handle that flow. So the weir has essentially been engineered to essentially prevent the wastewater and stormwater from going out unless the wastewater treatment facility is being overloaded. And here you can see water flowing over the weir and out into the river. And if you look a little bit upstream, you see that there is treated water from the wastewater plant, which is going out into the river, and it's all flowing downstream. It is obviously the combined sewer outfall that is causing the problem here. When we talk about 770 communities that have this problem, I've shown with black dots here the cities in the US over a population of 50,000 that have CSO problems. You can see that there are plenty of states in the Midwest that do not have any CSOs. And in fact, states that have a lot of big cities, but they are recent big cities, like Phoenix, for example, and Las Vegas and Reno, those cities were developed late enough so that there were separate sewer systems developed because we were aware of this problem. You can see Denver is another one that does not have an indication of a CSO. Salt Lake City doesn't have an indication of a CSO, and so forth. And all of the recent development in Texas also has been accomplished without combined sewer overflow problems because of separate sewers. So it's really those of us, say from, it looks like from, Kansas City and Omaha and Des Moines, Minneapolis to the east is basically where you're going to find the combined sewer overflows. And I see that Chicago is in there. I see Evanston. There are a lot, Gary is in there. You see that there are a lot of recognizable cities, over 50,000, that have a combined sewer overflow problem. And since I picked on Chicago, I will also say that Syracuse is also on the map, as well as Rochester and Buffalo. So we have our problems in New York State as well with combined sewer overflows. Smaller communities are the white circles with a dot in them, and you can see that there are a lot of those. So what are the traditional gray infrastructure methods? Well, those are mostly things like storage tanks and large pipes. And in the case of cities that were built up more recently, there is separation of the sanitary sewers and the storm sewers. There are also regional treatment facilities, meaning that you can build additional wastewater treatment plants in order to solve the problem. I'll point out that that's not a very efficient way to do things, because what you're doing is you're taking a certain amount of wastewater, you're diluting it by many fold, and then you are conducting treatment on a diluted system in order to remove the contaminants, which, as most of you are aware, is a very inefficient way to do it. Before you do your treatment, you want to have your waste stream to be as concentrated as possible so that you can efficiently remove those contaminants. And okay, so this is actually a photo just a few blocks from my house in Syracuse. So this is right next to the Syracuse University campus. And to say that we have flooding is an understatement. Admittedly, we do not have flooding as severe as some other cities in central New York and other places in eastern United States, but we have our share of flooding, and this is a big problem for us. Okay, so what are the stormwater management plans? Well, Onondaga County, which is our county here in Syracuse, basically had its first consent judgment written in 1989. And essentially, this was a consent judgment that promised to remove 95% of the water volume in combined sewer overflows. 95% of the volume. That has since been amended 4 times, mostly because of the challenges in actually achieving 95% removal. And you can see what the important features have been of past plans. This was before the days of green infrastructure being popular. So all of these solutions were gray infrastructure solutions. And I want to point out the last bullet point here: rejected alternate plans that were supported by community groups. There was a lot of community resistance in Syracuse in the early 2000s. There were lots of demonstrations, and those demonstrations on occasion even had violence associated with them, because it turns out that most of the regional treatment facilities that were going to be built in Syracuse were all in neighborhoods of poverty and underrepresented groups. And so this is the opposite of environmental justice. What are the problems with gray infrastructure? Well, these sewage treatment plants are expensive to build and maintain. You have to keep using hazardous chemicals. They require large amounts of energy. And this is not like you're going to be able to change this easily. Once you build these sewage treatment plants, you're going to keep them online for as long as you can. So essentially what you are doing is you are committing a community to living with these odoriferous and unpleasant sewage treatment plants. And those sewage treatment plants, as I mentioned, are preferentially located in poor neighborhoods. Lots of demonstrations. The building that is in the upper right of this slide is the building that houses the mayor's office. And this is a demonstration going on. This one was around, it was in the early 2000s, I think around 2005, 2006. And the citizens groups really came out from all over the city in order to protest what the plans were. Okay, so what are the barriers to adopting green infrastructure? Okay, I want to point to the most important one, and that is the first item on this list: the inability to guarantee precise outcomes. The truth of the matter is that none of the elected officials wanted to take the risk that if we were to go with green infrastructure, that in fact, we would be able to satisfy the 95% amended consent judgment. Nobody wanted to take that risk. What if the green infrastructure would not perform as it's supposed to? What if it would die? You know, Syracuse I'm sure many of you know that Syracuse is well known for its snow. And we're very proud of having the heaviest snowfall of any city over 100,000 in the continental US, and in the most number of years. We don't always win the Golden Snowball Award. However, we have won the Golden Snowball Award more times than any other city for being the city with the highest snowfall. Well, people do not, there has not been enough work done with green infrastructure to know how all of the green infrastructure that started out being used in, say, Mediterranean climates would perform in a place like Syracuse. And so there are real risks associated with this. And you can read these other points, but essentially, the elected officials were not willing to step up and take those risks. Okay, so in fact, in Onondaga County, we had a big change occurring in the year 2007 when a new county executive was elected. This is Joanne Mahoney, and Joanne believed in green infrastructure, and she held a number of hearings with experts in green infrastructure. And if you look at the middle of the slide, you will see there that in Syracuse, we adopted the 4th consent judgment, which was the first time in the US that green infrastructure was listed as a direct legal requirement in the reduction of CSOs. We were not allowing the construction of gray infrastructure to reach that 95%. Rather, there was a certain percentage that had to be done with green infrastructure. And by the time 2009 came around, we had, because of the use of a certain amount of green infrastructure, but also gray infrastructure, we had achieved 85% reduction, and we needed 95%. And that's why the second bullet item on the slide says that we still needed an additional 10% combined sewer overflow reduction in the water volume. And by modeling, that was to be achieved 6.3% of it by green infrastructure. That's 247 million gallons per year, and 3.7% by gray infrastructure for 145 million gallons per year. This started the Save the Rain campaign. And within the first few years after 2009, there were over 200 major green infrastructure projects completed. And that also enabled Syracuse to claim the most green infrastructure projects per capita of any city. And in fact, EPA held their first National Green Infrastructure Conference here in Syracuse at the State University of New York for the College of Environmental Science and Forestry, SUNY ESF, which is in fact part of the overall campus where Syracuse University is also housed. Okay, so here we are on the green roof. We're now going to focus on some of the quantitative side of the work. There are 3 of my students who are working up on the convention center green roof. And in the background, you're seeing some of the buildings of downtown. The Syracuse University campus is, well, you can see the trees on it over on the right side of the slide. You can see that they're up on a little bit of a hill. That is the University Hill, and Syracuse University is there. And all of our data are actually beamed by line of sight radio from the green roof directly up to our campus. So we get our real-time data right in our offices at the university. This shows a diagram of the roof so you can get an idea of the placement of our sensors and also the placement of the roof drains. This roof is aimed to, well, the building is built north-south. So to the upper right corner of the slide, that is the north part of the roof, and the lower left portion of the roof, that big wall, that's on the south side of the convention center. And you can see all of the roof drains, which is where we're doing our monitoring on both the east side of the roof and the west side of the roof, plus our weather station, rain collector, snow collector, and various other collectors. We also have a lot of soil moisture sensors that are buried in the roof. Okay, this shows a cutaway view of the layers of this green roof, and those little green rectangles are temperature sensors. So what we do is we measure the heat flow through the roof by looking at the temperature and calculating the heat flux through the roof. And the bottom of this slide shows the metal decking, which actually is at the bottom of the roof and serves as the ceiling of the convention center exhibit hall. And we have additional sensors mounted inside the exhibit hall, and you can actually walk into the exhibit hall and you can see those sensors up on the ceiling, which is about 35 feet high. So this is a pretty high ceiling, but in fact, our sensors are quite easily visible. And I will tell you that we have had to do maintenance on those sensors. And this is not a simple matter. It involves bringing a lift truck into the exhibit hall. And I'm happy to talk about that some more. There are a number of stories to tell about that, I'm sure you can imagine. To do a water mass balance, we essentially look at the amount of precipitation. We look at the flow to the drains. We know what the soil moisture is, so we can estimate the amount of moisture being stored in the roof. And we have estimated the evapotranspiration using chambers. And we are doing additional research trying to use instruments like lysimeters up there. So in fact, we are able to put together a rough water mass balance. I want to point out these drainage conduits, which are those diagonal lines that you see. Each of the roof drains has a roof conduit that is going over to the drain. And when the roof was constructed, it was constructed so that there is a 1% slope between the middle of the roof and going down to the roof drains on each side. That line in the middle of the roof that goes north-south, that is the peak of the roof. Here you can see us working with the construction crews when they were building the roof and were installing our sensors. You actually have to be there when they're constructing the roof in order to do this kind of work. There's one of our temperature sensors. Here's after the sedum has been blown using a big air gun onto the roof, and the sedum is growing. This is March 2012. Here's October 2012. The sedum has taken hold. You can also see the irrigation lines. This is a picture taken from a lift truck. Okay, this is right near one of our 3 mag meters, and essentially the water generally flows through that lower pipe, and that red box is essentially the computer link to the mag meter right below it. The upper part of this contraption is an overflow pipe, and I'm happy to say that that overflow pipe has never been used in the 10 years since this has been constructed. Okay, a 21-month study was one of the first studies that we did. This is 165 events. Because of the lack of time, I won't go into a lot of detail here, but we were able to do a lot of quantification with this study. You can see the overall retention performance. The green part of these bars is actually the amount that is stored in the green roof and that evapotranspires. So that's essentially the flow that never made it into the combined sewers. On the other hand, the yellow is water that made it into the combined sewers and that caused combined sewer overflows. Very small storms, of course, are completely recovered by the roof, so there's no combined sewer overflow. But even small storms, as opposed to very small, can cause some combined sewer overflow. Medium storms have more, large storms have a lot. So this is not a perfect solution. And we did a lot of analysis. This basically shows the rain and the runoff. The runoff is the black bars, the rain, the brown bars. This is an individual storm analysis. We do a lot of individual storm analysis looking at both the rainfall and the runoff. We also do a lot of soil moisture analysis, and this just shows one particular storm when we were watching the accumulation of water build up in the soil and how much water was being intercepted by the drain conduit. And again, there isn't time to go into detail here, but there's a lot of analysis that we're doing on using the soil moisture. And then lastly, I wanted to mention the HYDRUS modeling that we've done. My guess is that many of you are familiar with the SWIM model that was developed by EPA. And I'll say that we started out using SWIM for modeling the convention center green roof. We found some very important characteristics of the green roof as a result of SWIM modeling. And we found some very important characteristics of the SWIM model. We were not able to reproduce the data that we were getting on retention and runoff using the SWIM model, using what I would call reasonable model parameters. We had to resort to extreme model parameters that were not representing the real world, but rather were just being used to calibrate SWIM. And as a result of that problem, we switched over to HYDRUS. Now, HYDRUS does not have the same kinds of capabilities that SWIM does. So we're not able to do everything with HYDRUS that one can do with SWIM. However, HYDRUS is working using parameters that we measure and that are real world parameters. They're only giving us rough agreement, but nevertheless, we're getting rough agreement. And here I've listed the inputs and the outputs. Okay, this shows an example of data. I want to point out that the green line here is rainfall as a function of time. Okay, this is 5-minute data. So we are measuring the average rain intensity over a 5-minute period. And for this particular storm, which was on September 17th, 2016, you can see that those green lines show that it was a very complex storm. This is actually brand new analysis. We are just doing this analysis with all of our data. As you can imagine, we have gigabytes of data going all the way back to 2014, and we are using storms with selected characteristics in order to do our HYDRUS modeling. So this is recent modeling, even though these are old storms. And by the way, our data collection has not stopped. Now we've got lots more gigabytes of data. So there's a whole lot of work to be done here. The yellow line or gold line here is the HYDRUS modeling. And what's especially interesting here is that the HYDRUS modeling seems to follow the rainfall very closely. The black line that you're looking at is actually the measured runoff using that mag meter that you saw a picture of. Note that the roof does not become saturated until, with this rainstorm, about 6 hours after the rain started. So after 6 hours of rainfall with these ups and downs, suddenly the measured runoff begins. And you see that we have a large peak of runoff, and that corresponds obviously to the large peak of rainfall, which essentially put us over the bar in terms of saturating the roof. And you also can see that there is a time lag between when the rain peaked, which is also when the HYDRUS modeling peaked. In fact, I'm not sure if you can see, there's a tiny bit of green representing the rainfall, which is right underneath that HYDRUS curve. And the peak for rainfall was exactly the same as the peak for HYDRUS, within plus or minus 5 minutes. On the other hand, the measured runoff was about 15 to 20 minutes later. And we have seen that repeatedly. So we know what the time lag is between when the rainfall peaks and when we measure the resulting runoff as a result of the roof drains. It shows you that there can be a long delay in getting that runoff when you've got a 1.5 acre green roof, and the flows are quite complex, as you can imagine. If you look at the last major peak, which is, well, the third major rainfall peak, you see that all three of the peaks line up. You've got the rainfall peak, the HYDRUS peak, and the measured runoff peak. And therefore, the roof now has verified that it's been completely saturated, but we're still getting a 15 to 20 minute lag time with this. So there's a lot to go through with this graph, but I think it demonstrates that we are beginning to understand the green roof, and we are able to use HYDRUS to get a reasonable idea of monitoring of the runoff. However, until the roof saturates, we don't really have a reliable model. Lots of other curves. These are all brand new, by the way. These are brand new curves that one of my graduate students has just obtained. And you can see that the rainfall, the modeled runoff, and the measured runoff are all identical. I can see that we are running out of time. And so.
Can I actually break in with an audience question relevant to these graphs?
Absolutely.
Right. So there's a question about the equivalent runoff coefficient for the green roof. Were you able to determine that?
That's a really great question. And I have a PhD student working on that right now as we speak. And in fact, she's already made some progress. So within a matter of months, I hope that we'll have a paper out.
Oh, great.
On that. So that great question.
Terrific. And I didn't want to cut off the rest of your slides. We are running out of time and have a great queue of audience questions. So I'll leave it to you to wrap up as you see fit here, but I do want to make sure we get to some more of these audience queries.
Okay, in that case, I think what I'm going to do is go right over to the conclusions. You can read these conclusions, which is the results of the HYDRUS modeling. Basically, they confirmed what I've already said, that essentially we can do some modeling and we can get some approximate results. These are just some pictures of my students. We do a lot of work in the winter. And this is the same graduate student, by the way, who's looking at the runoff coefficient. And she's a very intrepid explorer. And there's my group up on the roof. And here are the conclusions. And you can read these conclusions. I will not take the time to show the real-time website where we have live data coming from the green roof, unless there's a question about that and somebody wants to see it. But essentially, I think that most of the points have been made. I will mention one thing more, and that is that one of the suburbs of Syracuse, which is the Solvay school system, has decided that they want to use the real-time website in their science classes. And so we are right now working out the wireless connections for the Solvay schools so that the science teachers will be able to use that in the classroom. So I will stop and take questions.
Great. Well, thank you so much for this fascinating presentation. And I know many that are tuning in will be interested in following that real-time data as you're able to make that publicly available. I'm sure you've got a built-in audience here for that. So I know there were several questions about the sensors, and you predicted this, the sensor layering, when were the sensors placed, what type were deployed, and what's on your dream development list for future sensors?
Well, I will say that the time scale for this was that this green roof was constructed in the year 2011. And this was essentially the reason that I moved from Carnegie Mellon up to Syracuse, because the county executive was, as I mentioned, really excited about green infrastructure, and she really wanted to have research done on the green roof. And let me tell you that having the county as a team player in this kind of research is just a wonderful opportunity. And it would have been impossible to do this work without having the county not only behind it, but actually fighting for it to make sure that it would get done. So the roof was constructed in 2011. The sensors started going in 2011. It wasn't really until around 2014 or 2015 that we were able to get regular data coming reliably from the roof. And indeed, a lot of the most interesting data starts in around 2016. We are still putting sensors in the roof, and I won't take the time to dream about what other sensors I'd like to put in, but let me tell you, the list is long.
I bet. We have a sensor project of our own, and that's like a dream features list a mile long, so I totally understand. So I guess I'll wrap it up with a combination of some questions kind of about the bigger picture. So you spoke so much to the performance of this green roof and avoiding stormwater runoff, huge problem, obviously, that we all need to care about. Are there other issues that green roofs can help. I'm thinking in particular about managing urban heat island effects, and just other energy performance targets that you're interested in understanding. And then follow on to that, what are some of the modeling capabilities we need to build to be able to understand, the economic benefits of something like green roof, if it's, not only on water, but also on energy and so many other things. So.
Wow. Well, so Elena, you have tapped into my dream list. I would love to be able to look at the ecosystem that's developed up on that roof.
Mm-hmm.
And I'd love to be able to look at how this green roof has affected the urban heat island, because obviously 1.5 acres in the middle of downtown is going to have some impact. I guess there's just a whole lot that could be done with this green roof. However, the lowest hanging fruit was in fact the stormwater management.
Yeah.
And frankly, I'm really glad that we focused on that.
Yeah.
And by the way, the data from this green roof, as well as from the 200 other green infrastructure projects around the city, helped Syracuse become in compliance.
Yep.
With our amended consent judgment.
Yep.
So this was actually achieved, I think in around 2018, something like that.
Yeah.
So it was a success story.
That's a big win. Yeah, and certainly understand. We're also glad you focused on the water angle, of course, being current, but we also, it's been a running theme across the Third Coast Water Seminars, certainly, but in our work, just the complexity of these kind of co-benefits of, water and energy, and how all of that is so important for all of our cities achieving our climate goals, right? So it's just an incredible frontier of science. We're so excited you are with us today to share this success story from this one project, and we look forward to staying in touch with the progress.
That's wonderful. And let me just make one final comment.
Sure.
Is that this is a success story in terms of achieving the amended consent judgment. However, let me say that this is not without controversy. Mm-hmm. And, in the interests of academic integrity, let me say that achieving the amended consent judgment is based on a combination of measurements and modeling. And there are a number of individuals who are highly critical of whether, in fact, we really did achieve the amended consent judgment, given its dependence on modeling. And so I just want to put up there, as truth in advertising, that there's still a lot of work to be done on this.
Yes, appreciate that. That's an excellent disclaimer. And I think anyone listening to this or watching this presentation who works within modeling uncertainty and works towards ever greater precision of models will certainly understand that and appreciate that. So I do, for sure. So thank you again for joining us. I'm going to close out quickly here, just sharing a little bit more about upcoming events that you can tune into. Please save the date. We have a very exciting week of events starting October 11th with Chicago Water Week. So we still are accepting event partners. If you're interested in hosting something, you can scan the QR code on screen and sign up to join us and become one of our 2021 event partners. We'd love to have you. So we also have our next Third Coast Water Seminar. School's certainly back in session here, so please join us September 29th to come hear about avoiding biofouling and scaling in reverse osmosis and nanofiltration systems. That's a mouthful. So we look forward to seeing you here and always on the Third Coast Water Seminar Series and in currents events. Thanks so much for joining us today. We'll look forward to seeing you soon.